Raul, that's Andrew, and Chris, and our project was a motor sensory system. So basically when we think of engineering and we think of systems, we think of their output. How much work gets put out of them, their output, basically output, 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 but a lack of emphasis is put, however, on the input from the system, which is just as important. Take, for example, what we were put to focus on was the electric motor. Usually large electric motors are ran without regard, with improper parameters, and ultimately what ends up happening is that they don't survive their factory life and are ran extremely inefficiently, which will cause the plant a lot of money, which is waste. So basically that's why we see electric motors like crying babies. We know that there's something wrong with them, but they can't diagnose themselves, they can't communicate with us. So right now, preventative maintenance standards, according to ASHRAE and ACCA, all it requires is a technician to look at their electric motors and HVAC plants, just by a quick visual inspection, listening for weird sounds, and just a quick glance at a dial gauge. Once again, this maintenance is completely non-comprehensive and is only done momentarily. So that's why our project objective was to create a motor sensory system that's going to be easily deployable, cost efficient, completely comprehensive and wireless, and will eventually be tested in FIU's HVAC chiller plants first. So a quick introduction, this project was given to us by Entech. They're an energy savings optimization company. They eventually gave us internships and postgraduate job offers. A quick guide of how we kind of formulated our project. We did begin with extensive research. It helped us pinpoint the faults and symptoms of failing motors. We then went through a final component selection. They had to meet certain criteria. We did analysis and experiments once our prototype was constructed, and then ultimately we checked for proof of success of our prototype. So kind of a timeline that we tried to adhere by. We did stay relatively on schedule. We did deviate by some days, but all in all, we stayed pretty much aligned. As far as tasks assigned, we did take major roles in certain tasks. However, we did get our feet wet and everything. We kind of a quick intro to kind of the sources of failure sources and symptoms of these large electric motors. When we look at thermal aspects, the first giveaway is low resistance in the insulation. So what happens is these copper windings start losing resistance, and ultimately they'll eventually burn out. A worn bearing or broken bearing is going to cause an increase in temperature in the shaft, which can be measured and will ultimately lead to failure as well. Talking about vibrational symptoms, definitely if you got an abnormal vibration, it is a telltale sign of failure. Usually these can come from maybe a misaligned motor shaft, loose mounting, broken rotor bars, stuff like that. As far as sensor selection, they did have to meet certain criteria. They did have to be low cost, open source, because we wanted to do the programming ourselves. It did have to be accessible worldwide. They did have to pass their feasibility assessment, so we did test all the sensors that we chose, and it also had to be completely non-invasive to install. That way, no hardships in that. We ended up finalizing our selections with the Arduino, a current transducer, a thermistor, and an accelerometer for our prototype. We chose the Arduino because it was something that I really wanted to work with. What it is a small computer that runs a microcontroller. Basically, a quick description of what it does, it lets you interact with the real world and the digital world, and vice versa. So it's a really versatile tool. It is low cost, it's open source, it is accessible worldwide. As well, it did meet our environmental standards. It is made out of non-toxic materials and recycled components. The sensors we ended up finalizing with to be the main inputs of our system. We went with the AXDL345 accelerometer for the vibrational aspects. To mount our thermal symptoms, we're going to be using a thermistor, and a current transducer to monitor current draw. As far as construction is concerned, it did give us a chance to work with Entech's electrical engineers, and it also gave us a chance to work with some pretty cool cutting-edge new tools, like the prototype circuit board printer that we got to use, which was the first time we had seen it, as well as 3D printers and really strong software such as LabVIEW. So our proposed final design, the inputs of the system is going to be the thermistor, the ADXL accelerometer, and the current transducer going into the Arduino, which is going to be programmed as their main data acquisition component. It's going to be controlling our inputs and our outputs, and then everything's going to be processed through LabVIEW or through the Arduino software. We did write our coding. We wrote it from scratch. Didn't include the calibration analysis that we will explain in a little bit. It also had to be organized nicely, so we organized it nicely so that way it's easier to process after. And so this is our final prototype. On the top is that printed circuit board that we use the mini CNC machine for. It is to IPC standards. We made it so that the top two inputs are for the current sensors, the top two inputs are for the accelerometer, the bottom two inputs are with the thermistor. That way we have two sensors inputting to the system every time. And then everything is plugged into the Arduino, which is our main communicator. So all in all, our prototype came out to only $110, which is it's significantly lower than having to buy a new motor, or even hire professional technicians to come and diagnose your motors.
All right, so the experiments were done to validate the analysis done in the project. It was to find faults in the prototype, and also make sure that the sensors and everything are sensitive to the system. So our thermistor experiment was done by going to the FIU chiller plant, having three of the same motors with the same loads and same input values, and installing the system and having it run for 3.5 hours.
So first we had to do a little bit of analysis into the calibration of the temperature. Since we were going to monitor the exposed winding at the surface, we did want to know, however, since the hotter temperature is located inside the surface, we wanted to see if we could calculate the difference in temperature between them. That way we could actually get the true heated temperature reading. We did first manual calculations, and we also did simulations, and we finally were able to calculate a trend line to the difference of the outside and the inside temperature of the winding. That way, once again, we catch the hottest part of the winding
So to do the install for the thermistor experiment, we created a magnetic thermistor holder that goes over the motor's vents, as you can see here, but does not obstruct the vent. And then we place the wire through there with the thermistor connected and with the strain relief. Here we have the three motors here where we did the rear end, the shaft end, and then we recorded the ambient temperature. And then here we compared the shaft end and the rear end. As you can see, motor 1 has a higher temperature, so therefore our system proves that it runs at different temperatures and will show faults.
To test the current draw experiment, we wanted to see if our system was going to be capable of being able to catch sensitive current increase in draw when extra load is applied. So we installed the current transducers. You can see where we actually installed it in our test motor after the driver. And this is kind of an installation guide of how it would be. Since it's a 3-phase motor that we'll be using, we'll put a current transducer around every input phase, so that way we get an average current reading. We had to construct first a apparatus to simulate a load. We wanted to do it in a way that we'll be able to calculate what our load is. So you can see through our system that when we apply a torque on the nuts, we get a force on the shaft downwards. Between the shaft and the force downwards is a brake. Knowing all the coefficients between the brake and the materials, we can then calculate what our simulated load is and calculate every step of the procedure. This would be every step of the procedure calculated and our range of torques. We made sure that our torques were tied into spec with our torque wrench. That way we could make sure that our results were accurate. So ultimately, this is what we ended up finding. We tested, we changed the driver settings from 20 hertz to 30 hertz. That way we could see, as we expected, as load is increased, our system was able to catch an increase in current draw. And we did this, as I said, for every hertz, and for every frequency of the motor. And ultimately, what this gave us, ended up being surprising for us, was we were able to calculate and find trend lines for each of these. So now these equations here prove very vital in the real world, because when our system catches an increase in current, since we have the relationship, we can now calculate what the increase in load was applied to the motor. So usually these increases in load come as a surprise, because it could either be internal resistance of the motor due to failure, or even in these HVAC plants, what happens is that the pumps that they're running will build residue inside of the pumps and will cause more resistance inside of them. So that way we could actually calculate exactly what it is.
So the cost analysis was provided for an estimate of the cost per year to run versus a healthy motor and unhealthy motor. And the red is the unhealthy motor, and then the orange is the healthy motor.
And the only difference is a 3 amps difference. So even a motor running at 3 amps more than the other will result in drastic spending of the year.
So this vibration experiment will demonstrate the capabilities of our system combined with Arduino LabVIEW processing. Initially, the accelerometer will be attached to the motor with no load, and using the VFD, the variable frequency drive, the supply frequency line will be adjusted, and the motors with an induced knock and an increased induced knock, their vibration frequencies will be analyzed. So here's a nice little simulation of the FFT. What the FFT does is it gives us, this green distorting signal is a combination of two different frequencies that we're able to see here, and then translated into the frequency domain where we're able to see the two resulting frequencies coming from the signal. This is our LabVIEW coding that we wrote for this project to analyze vibrations. This first red square introduces the accelerometer and Arduino's LabVIEw. The second red square is 128 iterations of the raw acceleration data being output into a for loop. And this third red section here is where the FFT function outputs the waveform route. So we will be comparing our experimental data, our experimental vibration frequencies to the theoretical frequency vibration, which is equal to twice the line frequency. So mounting locations are very important for this experiment. We must ensure that the accelerometer is placed along the midline of the motor to ensure accuracy of the results, and that it is directly in contact or into a threaded hole, as pictured on your right, to ensure accuracy of the result. So here's an example of our motor with no load. We successfully managed to record a experimental frequency of 41.2 hertz, which has a 2% error compared to our expected frequency of 40.8, which is twice our line frequency. Now the sound you hear is a motor with an induced knock. That experimental frequency again was very close with a 1.27% error compared to our expected frequency. However, that induced knock that you just heard had an amplitude of 600 millimeters per second squared, with a lower frequency of about 32.55 hertz. Now the sound you hear again is the same motor with the same knock, with the same frequency. However, the magnitude is increased. So our system was successful in catching the frequency, our experimental frequency, compared to our expected frequency, and with a small, very marginal percent error. So to conclude our vibration experiment, we were successful in observing changes in magnitudes and frequencies as well. Some future recommendations would be to run the VFD or variable frequency drive at higher frequencies and observe the response.
In conclusion, we can say through our experiments that our prototype was a success. We were able to highlight and showcase symptoms of failing motors. We did become familiar with the growing field of real-time building management systems as well as preventative maintenance systems, which is something that we are interested in post-graduation. We did gain a cognitive understanding of data acquisitioning and their processing, as well as provide insight on sensor capabilities, their applications, as well as their implementation. As far as global aspects that was kind of used during our experiment and kept in mind, we did keep our components open source as well as easy to access worldwide. As far as our processing and our manufacturing procedures, it is available worldwide also, and is easy to do. We also understood that there is a global need for energy savings policies set by the International Energy Association, which is a committee of 29 of major countries. They do a very scrutinized analysis of how much money countries would save if plants did run specific policies in their plants and energy efficiency policies. So experiences gained, we did get to work alongside NTEC's multidisciplinary team. We got to get our feet wet with the electrical engineers as well as the programmers. It was awesome being part of their really motivated team. They're a small team, but they really do strive to create some innovative products. We got to work with some pretty cool cutting edge tools. Learned a lot about project organization with new techniques for it, as well as long-term teamwork. And since this is an ongoing project for us, and we will continue to do this, there is still future work that has to be done. We do have to store and redirect our data into a bigger server. We do have to make the system, the prototype wireless. So we did make our design already compatible with the XP, which is going to be our wireless communicator. We will work on the output for the customer. So basically a dashboard letting them see a real-time analysis of their system, which will prove vital for our customers. And also create an alarm system in our coding, just to give us an alert if anything real drastic is happening, as well as visit more plants for more general information. That's it.
comments?
I want to applaud you guys for tackling one of what I think is really some of the under-attempted items in mechanical engineering when it comes to instrumentation. It's pretty rare, but it's pretty integral into systems nowadays. I guess my question comes from what's the expected reliability of these components? They're looking for long-term solutions, I'm assuming.
Well, as far as calibration with the accelerometer, for instance, once the accelerometer is calibrated for a specific motor, it never needs to be calibrated again.
And since they are cheap too, also in our system, I don't know if you want us to bring back to the prototypes, but when we showed the inputs for each of them, it's a real easy system of just taking out the wire and replacing it with a new sensor, if anything. So as far as maintenance, it's going to be real quick to just put in a new one. But they should be reliable with cheap parts as well.
The thermistor is just a resistor, so it's very cheap.
Right.
and easy to-
Our goal is to really to create a system that will be useful, just out of ordinary parts and cheap parts.
Intech, they bill their customers by the data that their system generates.
Yeah, they don't
So-
charge them for the actual system,
Yeah, right.
whereas they charge them for data.
So Intech doesn't want to spend a couple thousand to plant something and then they're not getting that back. But they don't want to charge the customers, so therefore we have to find the cheapest way to get all the results.
Any questions?
How did you get this project?
If you want the real story,
Yeah.
so
All right, so the CEO of this company actually goes to my gym, and I saw him on the floor. He was out of breath, and I said, "Hey, let's go, let's get up." And then he came back to me a couple months later and said, "Hey, what are you doing? Were you studying?" I mentioned, "Yeah, I'm studying mechanical engineering, this and that." And he said, "Come on board, I have a project for you." And that just came around when we had senior design.
resulted in job offers and internships too. So we
And
got
are
real
they
lucky.
in
with that.
Miami?
Yeah,
Yeah,
they're
they're
Miami.
More
So what is their major business?
So right now they're in the Trump Towers, all the Trump Towers. They're in
Marlin
Stadium,
Stadium.
the
So
hospital.
So they evaluate
So what
the
they
efficiency
do
of
is
the motors?
of the HVAC
Of the
systems.
HVAC system.
Yeah.
We were tasked with.
This is their side project that they want to start
Oh,
Yeah.
so they already are evaluating the efficiency
Oh,
of
yeah,
what?
using. Like the flow.
The HVAC system,
Oh,
heating and
HVAC,
ventilation.
I see that.
Specifically the chiller plates.
Right.
And they've been working, they were doing the internship actually at this company. Now they all have offers for full-time jobs.
Are there going to be patents flowing from this?
Oh yeah, these guys jump on patents real quick. They probably have one already.
They don't want me to publish.
We're not too familiar with it right now.
Oh.
but,
So will
uh,
FIU benefit from the patents?
Oh yeah, well the first location
Yes,
since
right.
Antec did get hired by
No, I mean
FIU.
financially.
Oh. But FIU will be the first system to be acquired with these prototypes. So that'll be pretty cool, I guess.
Very good.
Wow, that's
Congratulations.
good.
Thank you.
Thank you.